Hello everybody. Today we are going to be working out of the notes packet. So if you have to pause this video, pause it until you get this packet out, whether it's on paper or you have it in Kami, but this is the one you want. And we are working on the third page. So the top of the page has the metric conversion chart. We're working below that. We're going to finish this page. Okay? That's what we're getting at. So, equations involving metric. Since we've been talking about metric prefixes, I want to make sure you are using them right when we use them in equations. So you want to copy down the stuff that's going to come up in blue. So, area. The equation for area is length times width, something that I'm sure you've heard before. You just have to remember when you're doing it, you want to pay attention to what units you have. So, for example, if the length and the width are both measured in meters, when you get your answer, you have to include the unit of meter squared. Or if they're both in centimeters, whatever the case is, you have to put them squared. They should be the same unit, though. You shouldn't have one in meters and one in centimeters. You want them in the same unit. Same kind of idea goes with volume. Volume's a little more difficult. You're talking about length times width times height. So this is for a regularly shaped object. So a cube, for example. You could measure the length, the width, and the height, multiply them all together. The SI unit is meters cubed or centimeters cubed. They're the two most common ones that we are going to see. Now it's cubed. For example, if you have the length in meters, the width in meters, and the height in meters, you get meters cubed. Or if they're all in centimeters, you get centimeters cubed. The non-SI unit would be liters. That gets used sometimes too. And the reason for that is if you have a cube that is 1 centimeter by 1 centimeter by 1 centimeter. So if the length is 1 centimeter, the width is 1 centimeter, and the height is 1 centimeter, you would be able to fit 1 milliliter of water into it. So 1 cubic centimeter actually ends up being the exact same thing as 1 milliliter. If you're ever watching a show based in a hospital and you hear them say, like, I need 10 cc's of whatever, the cc is just their abbreviation for cubic centimeter. So if they say they need 10 cc's of something, that's like saying they need 10 milliliters of something. All right, so a cubic centimeter and a milliliter are the same thing. Now, density is another equation we're going to work with throughout the year. Density is mass divided by volume. That SI unit is typically grams per milliliter. If it's a liquid, it is grams per milliliter. If it's a solid, a regularly shaped solid that you had to measure the volume of, the length times width times height, then it becomes gram per cubic centimeter. But in reality, those two things are equal. Right, if something has a density of 10 grams per milliliter, it's also 10 grams per cubic centimeter, because a milliliter and a cubic centimeter are the same. Some other values we're going to work with throughout the year are temperatures. Celsius, which is actually what we're going to use in the lab, or whenever we talk about temperature, is actually not the SI unit for temperature. Kelvin is the SI unit for temperature. So the conversion from Celsius to Kelvin actually ends up being really easy. All you have to do is add 273. And the reason for that is that a change in 1 degree Celsius is the same as a change in 1 degree Kelvin. So you have that scale that's going up at the same amount, which is different than Fahrenheit. A change in 1 degree Fahrenheit is not the same as a change in 1 degree Celsius. So if you had a class before, like physical science, I know did this, converting between between Celsius and Fahrenheit was a more complicated equation where you needed a fraction and all that kind of stuff. Celsius to Kelvin, though, is really easy. Just add 273 and you're done. All right, so some common temperatures. Freezing point of water. Most people in the U.S. are used to saying 32 degrees Fahrenheit is the freezing point, but it's also 0 degrees Celsius. And notice whenever I do this, the Kelvin temperature is always bigger than Celsius, and it's always bigger by 273. The boiling point of water, just for a reference, is 212 degrees Fahrenheit, 100 degrees Celsius, but it's 373 Kelvin. Again, notice you just add 273 to go from Celsius to Kelvin. Human body temperature, usually 98.6 degrees Fahrenheit for most people, 37 degrees Celsius, and 310 Kelvin. Now, this is not important. I just usually have people ask me. I don't know why they don't use the word degree or the degree symbol with Kelvin. If you did, I wouldn't care. It's not like I would take points off or mark it wrong or anything. But notice when I'm saying them, I'm saying like degrees Fahrenheit, degrees Celsius, and I just say Kelvin. For whatever reason, that's the way to do it. Absolute zero. Now, absolute zero, and if you want to, pause the video after I say this to write it down, because you'll want to know this. Absolute zero is the temperature where all motion stops. So temperature is really just measuring how fast particles are moving. The faster the particles are moving, the higher the temperature. The slower the particles are moving, the lower the temperature. Absolute zero, in theory, is the coldest temperature that we can get to, because that's where they say all motion would stop. Right? So if temperature measures how fast particles are moving, if there's no movement, then in theory you can't get any colder than that. So that's all the way down at negative 459.7 degrees Fahrenheit, negative 273 degrees Celsius, and 0 K. So some other temperatures that might help you get an idea of this scale. Room temperature. Most people say room temperature is 68 degrees Fahrenheit. It's where most people say they feel comfortable. So 68 degrees Fahrenheit, that is 20 degrees Celsius. Something that, you know, a lot of people would probably be considered like a hot or warm day, very warm day outside, would be 30 degrees Celsius. A lot of times people say that's on the hot side. So 30 degrees Celsius is around 86 degrees Fahrenheit. Just to give you an idea of the scale there. So here's a little graphic showing you some stuff. All right, so freezing point of water, 0 degrees Celsius, 32 Fahrenheit, 273 Kelvin. If you're able to get all the way down to 0 Kelvin, like I said, in theory, that is the coldest it can get because that's where all motion stops. And then I have the boiling points up here, just like the other slide. A density column. Since we're going to end up talking about density in a little bit, I just wanted to show you this because I thought it looked kind of neat. When you talk about density, density really dictates whether something is going to float or sink if you put it in water. And there's other ways you can demonstrate this. So somebody took these things and they poured them into this column very carefully. Honey is the most dense out of all those things, so that's going to be at the bottom. Lamp oil is the least dense, so that's going to be up top. And then everything in here just layers with the more dense stuff towards the bottom. So you'd have to do this very, very slowly to get this column to look right. So they took honey, put it in there, Caro syrup, put that in there, Dawn dish soap. Now water, they put a little bit of food dye in there just so you could see it. That's really like right in the middle. So anything below it is more dense than water. Anything above it is less dense than water. And it just settles out like that. It's the same way they make things called Galileo thermometers. Galileo thermometers, they kind of look like this, except with these little balls, they have temperature symbols hanging down from it. So it's just like a fun little way where you can figure out the temperature sometimes. You know, depending on how hot it is, the density might change a little bit. Well, no, the density doesn't change. The liquid outside will change the volume a little bit. So then the balls will either sink or float depending on the temperature. There, you can figure out the density of an irregular shaped solid, and we might end up doing a lab on this when we're back in person. So let's say you have a marble or a stone, something that you can't just measure the volume of very easily, like length times width times height. You would still be able to figure out the density of that if you had the right equipment. Remember, density is mass divided by volume. So those are the two variables you need to figure out density. The mass is easy. You can put that on a balance and get the mass. The volume is the tricky part for this object. What you can do is called a displacement test. You can fill up a graduated cylinder to wherever you want and read that volume. In this case, it was filled up to 20 milliliters. You drop that marble in there or whatever it is you're measuring, and that water is going to move up some because the water is going to get displaced because this marble is taking up some of that space. So in this case, the water looks like it went up to 25 milliliters. Well, you would just take the difference between those two numbers and say, okay, the volume is 5 milliliters. So you get the density from the balance, the volume you would get from a displacement test, you could do the division, and then you can get the density of whatever that object is. Examples of density problems. And I'm going to go through this, and we're going to do a lot of practice on this. So it's saying calculate the density of a 12.55 gram sample that has a volume of 4.65 milliliters. Now, if I could write on this, I can't. If I could, when I'm doing a problem like this, what I think is a good idea is to write down what these units are. Right? Density is mass divided by volume. So when I read this, this is grams, so that's going to be mass. So I would put an M above that. 4.65 milliliters is volume, so I'd put a V with that. So right now I have it labeled as I know the mass, I know the volume. That ends up being a pretty straightforward problem then. I could just take mass divided by volume, 12.55 grams divided by 4.65 milliliters, and that's going to give me my answer. I want the number and the units. And we could end up using this kind of information to ID or to figure out what some unknown solids may be. Right, so if I knew this was a piece of metal, a piece of pure metal, but I didn't know what metal it was, I could figure out the density of it and compare it. Now this is just a couple of metals, well-known metals. Aluminum has a relatively low density, 2.70 grams per milliliter. Right, and then as you move up on the periodic table, or I guess I should say as you move down on the periodic table, as you move up in atomic number, which we'll talk about later in the course, metals tend to become more and more dense. So by the time you get down to gold, that's 19.36 grams per milliliter, which is a lot more dense than aluminum. Right, so you can use densities to ID certain objects, because really what's going on here, it doesn't matter what size piece of aluminum I have. I could have a small piece or I could have a really, really big piece of aluminum. And if it's pure aluminum, I'm going to get this density, because whenever the volume changes, like if I have a bigger piece, it's going to be more volume, the mass is going to change at that same ratio. Right, same thing, if I had a really small piece of gold or a really big piece of gold, it's going to have the same density, 19.36. All right, now this one is a little different. What is the mass of a 2.73 cubic centimeter sample of silver with a density of 10.49 grams per cubic centimeter? Now this one's a little more difficult. When I look at this problem, I see this cubic centimeters, or centimeters cubed, however you want to say it, and that is a volume. So I would put the letter V with this. Now this is telling me is a density, and I know it's density because it's grams per cubic centimeter, which is mass per volume. So I would put a D with that for density. And what you have to do, and we'll end up doing a lot of practice with this, what you would have to do is take that density equals mass over volume and rearrange it to solve for mass. And the way you do that then is you have density times volume. And if I could write on this, I would show you me actually doing that work. So we'll have to do that another time, but that's okay. We'll go over that. When you're doing a problem like this, it helps to have the units in there, because you're going to see what units you should end up with. The centimeters cubed, since that's in a denominator, that's going to cancel out with these centimeters cubed, and you're going to end up with just a mass of 28.6 grams. All right, so this is one where you had to rearrange the equation, and we'll have to do that sometimes, and we'll go over it. All right, now this one is asking you for volume. A 39.46 gram sample, so I would put M above that for mass, has a density of 2.34 grams per cubic centimeter. So I would put D above that for density. Calculate the volume of the sample of silicon. All right, so if I take that density as mass over volume equation and I rearrange it for volume, I would end up getting mass divided by density. 39.46 grams divided by 2.34 grams per cubic centimeter. So now the grams would cancel out. The centimeters, which are in the denominator of a denominator, end up being the units, 16.9 cubic centimeters, which makes sense because that's a unit for volume, and that's what we are looking at, volume, we're looking for. Now another concept with this is if you were given different liquids and told their densities, you would be able to figure out how they would layer if you put them into a column. So like that picture before where it had the honey at the bottom and the lamp oil at the top, I think it was. Right, it's really just the more dense stuff goes to the bottom. So what you would get is B is the most dense, so that would be at the bottom. C is medium, so that would go in the middle, and 0.785, letter A, has the lowest density, so that would go up top. All right, so we're going to end up doing more practice with some of these equations. Just pay attention to the units and the numbers. Make sure all that stuff checks out okay. And we will go over this a little more in person.